Good morning, my name is Ben Schmidt from Physical Electronics. This was a paper presented at ECASIA 17 in Montpellier, France. And the talk focuses on using ion cluster beams to depth profile through inorganic and organic materials with the idea to give users practical operating conditions for these type of materials. Now, as we all know, monoatomic argon has been the primary sputtering beam for many years, and we are typically dealing with more and more materials that are multi-layer systems that do have features of interest below the usual XPS information depth of about 10 nanometers. And so if we want to investigate those deeper layers, we need to use some sort of depth profiling mechanism to investigate those surfaces. In particular, new materials are being introduced that combine both organic and inorganic components. For example, organic electronics, where we have organic active layers sandwiched between metallic electrodes or inorganic electrodes. We also have biomaterials, where we would like a biological system to interact favorably or disfavorably against an inorganic scaffolding, for example. And so if we try to use monoatomic argon to do depth profiling of such materials, what we typically find is that the damage in the organic layer is such that we lose all of the chemical information. As shown here in a 500 EV argon profile of PMMA on hafnium oxide on silicon, the PMMA layer does not show the expected composition. And so as alternatives to monoatomic argon, several types of cluster type beams have been developed. For example, the C60 cluster and also an argon cluster, which we'll call GCIB in this presentation. And each of them have their pros and cons. For example, monoatomic argon is very useful for metals and inorganic compounds, but as we previously mentioned, not very useful for organic materials. Whereas the C60 and GCIB work much better for organics for maintaining chemical information with depth. With the GCIB, for example, we do have the ability to tune voltage cluster size for a variety of operating conditions, and so the user is often left with many questions about what is the most appropriate method to use for profiling. And so in this work, we have three parts where we will start with bulk materials of polymers and hafnium dioxide, and then switch to an inorganic mixture of hafnium dioxide, silicon dioxide, and silicon. And then based on the results from those two situations, we will look at a mixed material, organic, inorganic, consisting of PMMA, hafnium oxide, and silicon. So to start with, in the bulk materials ion sputtering, we are using 4 polymers and hafnium dioxide. The polymers are PMMA, PTFE or Teflon, PET, and polystyrene. And we have 4 cluster ion beam conditions that we'll be using for this analysis. One will be a 20 kV C60 beam, and then 3 argon cluster beams, 2 at 20 kV with different cluster sizes, 1 at 10 kV. And so based on the voltage and cluster size settings that we have chosen, we will have a nominal energy per atom that has been shown to have an effect on both sputter rate and damage within materials. And as you can also see, for the GCIB, for these 3 settings, for PMMA, we see that the setting with the highest nominal energy per atom gives us the best efficiency at removing PMMA compared to settings with lower EV per atom. The 3 of those in general, if you compare to C60, even though the C60 has the highest EV per atom, we do see that it is not quite as efficient as removing PMMA, but it's within an order of magnitude. So we'll do some comparisons of those different settings. And this work was done on a 5 VersaProbe 3 instrument, where we have both the C60 and the GCIB and monoatomic argon all mounted on the same chamber. And so the idea behind the profiling is that we will profile the polymers to approximately 100 nanometers in depth. And what I'm using for that depth reference is PMMA. So whatever time is needed to profile to 100 nanometers of our PMMA sample, I'm using that same sputter time for the other polymers. So we may not get to exactly the same depth, since we know sputter yield is not the same across all polymers, but we would expect a similar depth. For the hafnium dioxide, we are profiling to approximately 60 angstroms in depth. And these films were fabricated at the University of Minnesota Nano Centers, and we appreciate their contribution. So what I'm showing on this slide now is basically the 4 different polymers, and I have overlaid the spectra of the end of the profile process. So we have profiled approximately to 100 nanometers according to PMMA, and I have 4 spectra overlaid on each of these figures, one from each of the ion gun settings that we referenced in the previous slide. And as we can see, the general shape in all cases is maintained. We see that there are oxygen-containing peaks, oxygen-carbon peaks still showing here. We see a shake-up satellite feature that still appears in polystyrene. So we have not lost the significant unique features of these particular materials. I can do we can assign a damage parameter, if you will, to each of these settings to look at how affected the polymers are based on this ion gun setting we chose. For the case of PET, I looked at the oxygen-carbon ratio. For PMMA, also the oxygen-carbon ratio. For the polystyrene, the ratio of the satellite peak to the main peak. And then for PTFE, the fluorine to carbon ratio. And we can see that for the GCIB settings shown here, that we maintain similar information across each of the settings. We also notice that for the C60, we have approximately the same damage, but slightly more. We're seeing that the oxygen, there's slightly less oxygen compared to carbon when compared to these other settings as well. But in general, we are maintaining the overall structure and shape of the peak of interest. We have also looked at the hafnium oxide, and in this case I have a hafnium oxide film that we sputtered to approximately 60 angstroms depth and use 4 different GCIB conditions ranging from 4 EV per atom in the top left figure to 32 EV per atom in the bottom right figure. And what we notice is that once we have the energy per atom at the setting of about 8 EV, we do notice there's a decrease in the peak intensity of the 4F5 halves peak, and we do see broadening to the lower binding energy side here. And that is also shown when we increase the energy per atom. So we do not see that. It is not apparent in the spectra for the 5 EV per atom and below. And this is in agreement with literature that approximately 6 EV per atom was a damage threshold that could be observed in the peak shape. We also notice that as we do increase the EV per atom, there is a decrease in the oxygen to hafnium ratio after sputtering, which is consistent with loss of oxygen as we increase the energy. So you may think that the best option is to always use the 5 EV per atom setting. One thing to consider is that as you go to lower energy per atom, the sputter rate is affected as well. So for the condition where we observe no damage, if we consider that as a 1x sputter rate, the sputter rate increases as we increase the energy per atom, whereas we do see a little bit of damage. So there is a trade-off there depending on the sample you're working with from a practical standpoint. So to summarize this section, with the polymers, we noticed that there was some damage observed at the cluster ion conditions that we used, but in general the main features of each of the spectra was maintained up to the highest operating condition of 333 EV per atom with C60. With the HfO2, we noticed that we did have a lower threshold before we saw any type of damage. And in the case, if we want to completely preserve the chemical structure and shape, we would need to operate it at about 5 EV per atom or lower. However, there is a trade-off between the damage and the sputter rate, which can affect the practical user. In the next part, we are looking at a strictly inorganic system of hafnium oxide on SiO2 on silicon. And as you can see in the bottom left of the slide, each of these are about 80 angstroms thick. So we have a total stack of about 16 nanometers. And we have compared 3 operating conditions. One is a 500 EV monoatomic argon, and then a 20 kV C60, and a 20 kV argon 620. And as we look at the the general profile. With the argon, we do see sharpest interfaces between the different layers. However, we can see that there is a decrease in oxygen in the hafnium oxide layer, and we also see that for the argon gas cluster, there is a very large, the hafnium signal extends deeper into the sample than the previous two sputter conditions. Let's take a look at what may be happening with this GCIB setting on the right. What I'm showing here are montage spectra, montage plots through the sputter profile. So this is the spectra collected at each sputter step along the way. And going from across the rows, so these three figures are all part of the 500 eV monoatomic argon profile, the hafnium 4s spectra, the silicon 2p, the oxygen 1s, and in each of these, the first spectra, so the surface spectra, is at the top. And as we profile through the material, we reach the bottom. And one thing we can see right away is that for the hafnium, we do see this broadening to the lower binding energy side, indicating damage. And if we compare between the monoatomic argon to the C60 to the GCIB, there is a decrease in this damage as we go to lower EV per energy, as shown by the lowest EV per energy, in this case being the argon cluster profile. Now, one thing that is interesting also is if we look at the oxygen spectrum. So starting in this area, this would be our hafnium dioxide oxide, and then this peak shift is representative of the transition into the silicon oxide layer. Now, with the argon gas cluster, we really do not see a dramatic shift, even though this was the same sample used in all three cases. This is currently under investigation as to what may be happening. One theory could be that if there is some damage occurring, that we actually may be reducing the silicon and reoxidizing the hafnium, in which case we would not see a silicon oxide shift on the oxygen peak and instead maintain a hafnium oxide-like bonding throughout. So that is something we're actually investigating right now. We have also looked at the extent of the hafnium 4F damage in the hafnium oxide layer, comparing unsputtered spectrum to that of a C60 and argon gas cluster. And we see that, as we showed in the last slide, for the C60, we observed the most broadening in the 4F spectrum and a slightly less broadening using the gas cluster source. We can also look at the carbon 1s spectrum to understand what that damage may look like. Using the argon gas cluster, we do not see any significant carbon contribution at this point in the profile. However, using the C60, there is a peak at around 281 EV, which would match up with a hafnium carbide. So what we may be seeing is some hafnium carbide formation that contributes to this broadened peak. Now, another test that we looked at was to understand how much of this damage is due to the ion sputtering or maybe just inherent to the sample in the deposition process. And we're using HAXPES, or hard X-ray photoelectron spectroscopy, to understand this in more detail. So for the stack that we have, which is approximately 16 nanometers, if we tilt our sample to 90-degree takeoff, so we should get the most information from the bulk of the sample, using our aluminum K-alpha source, our hafnium 4F peak is shown on the left. As far as the silicon 2p, we only see one peak at approximately 103 EV, which would correspond to that of an oxide. So it appears that we are only seeing into the SiO2 layer and not all the way down to the substrate. What we can use is an alternative X-ray source, such as a chromium K-alpha X-ray beam, which has a higher photon energy that provides us about 3 times the information depth. And this analysis was performed on the Phi Quantes system, which allows both aluminum and chromium analysis in an easy system. As shown with the chromium K-alpha source, we again have looked at this sample at 90-degree takeoff in the as-received state, so neither of these have been sputtered. And in the Si2P spectrum in particular, we see 2 states, one that would correspond to the substrate and one that would correspond to an oxide layer. However, we notice in the hafnium-4F there is really no change between the two sources. If there was some type of damage at the surface in the hafnium, we may expect there to be some type of shoulder on that, which we do not observe. And so we can assume that the damage that we're observing during profiling is representative of the profile itself and not something inherent to the stack. And so to wrap up the second part of this talk, we used, again, several ion beams to sputter through an inorganic stack material. We found that the best interface was defined with the C60 and monoatomic argon. However, we saw the largest amount of chemical damage using those beams. With the argon 620 GCIB setting, we observed the least amount of hafnium-4F chemical state damage. We're still investigating the effect of the possible silicon reduction, and we will do some more research on that. Now, in the last part of this talk, we want to look at a mixed inorganic-organic stack under several conditions that may work in both cases. So we've looked at a PMMA hafnium oxide silicon stack. Shown on the bottom left, we have a 200 nanometer PMMA on 20 nanometer hafnium oxide using both a low energy GCIB setting on the left side to a slightly higher EV per atom setting of GCIB, and then our C60 setting. And what we notice with the low energy GCIB, although that we expect less damage on the hafnium oxide as shown in previous slides, the sputter rate in the inorganic material is extremely slow. You'll notice that the difference between the PMMA and hafnium oxide sputter rates show more separation as we go from low EV per atom up to higher EV. So the C60 gives us approximately a 150 to 1 PMMA to hafnium oxide sputter ratio. PMMA to hafnium oxide is about 300 to 1 for the argon 620 and much higher for the low energy GCIB. And so if you are looking at trying to deal with these type of mixed materials, you want to be able to both use settings that provide adequate sputter rates for getting through your material in a reasonable amount of time and also minimizing the damage that you observed. I will point out that I did intentionally reduce the sputter rate by extending the raster size of the beam and decreasing the current in order to get enough data point density in our carbon PMMA layer due to the extremely high sputter rate. So we can increase that if desired. And now I want to look at the early stage of the profile for these three materials. And you can see again that the 200 nanometer PMMA layer can be sputtered through in just a couple minutes. So it is very fast under these conditions. And we do notice that nominally we are preserving both the PMMA and hafnium oxide stoichiometry for each of these settings. When we look at these on a depth scale, comparing primarily the C60 and the high energy GCIB, we notice that the interface is slightly narrower with the C60. However, there is inclusion of carbon of about 5 to 10% in the hafnium oxide and silicon substrate layers, whereas we noticed negligible, if not just a percent or so, of carbon using the GCIB setting. We also look at the oxygen to hafnium ratio for the hafnium oxide layer, and with the GCIB we are maintaining approximately the about 65 to 70% oxygen that we would expect. However, for the C60 we can notice that the oxygen is around 60%, so we are losing oxygen within that layer. So to conclude, for the last part here, we looked at 3 settings, 2 GCIB settings and 1 C60. We find that the C60 provides the sharpest interface and speed. However, we have observed that there is more chemical damage, and we also have the contribution of carbon into the film. With the low energy GCIB, we observe less damage, however, at the expense of a very slow sputter rate. The high energy GCIB, the argon 620 cluster operated at 20 keV, is a promising candidate that allows us to minimize damage while maintaining a reasonable sputter rate. And so hopefully these settings will provide some insight into usable sputtering conditions for depth profiling through bulk inorganics, organics, and mixed materials. Thank you.